Bismillahirrahmanirrahim. Assalamu alaikum. In our last lecture, we talked about the Newton-Raphson method, and in our today's session, we'll be discussing about the secant method. And as usual, first of all, we'll be describing the procedure of this method, and then we'll be solving a question at the end. Now we take start the procedure of the method. The title of the method is the secant method. This method starts from a function whose root we are looking for. And here we require, if you remember in the case of the Newton-Raphson's method, we require only one initial starting guess. So here for this method of secant, we require two initial starting guess. And we label them as x0 and x1. And now how actually the method proceeds. We take start from the Newton-Raphson's formula and our method's formula, which we had derived in our previous lecture, and the formula was xn plus 1 is equals to xn f of xn over f prime of xn. And when we derived this formula there, I told you that this derivative appearing in the denominator is a major problem. Now we are going to replace this derivative with a difference relation, and the difference relation which we are going to use here is of the form fxn minus f of xn minus 1 whole divided by xn minus xn minus 1. So this is the difference relation we are going to use in order to replace this derivative, and whenever we substitute it into this formula, we get xn plus 1 is equals to xn minus f of xn whole divided by the whole difference relation. So here we write down f of xn minus 1 whole divided by xn minus xn minus 1. Now you have to simplify, and whenever you simplify it, you will be getting a beautiful result. Keep this information in your mind. Okay, now we are going to simplify this. Whenever you simplify, the simplified form of this result will be looking like this: xn minus 1 f of xn f of xn minus 1 whole divided by fxn and minus f of xn minus. So this is the ultimate result we are getting after simplification of this last result. And here n starts from 1 and onward. You can see here we are taking start from 1, while we have taken start in the case of NR method from 0. And now if you substitute n equals to 1, suppose we take n equals to 1 in this formula, what do we get? On the left side there will be x2. On the right side we get n. Whenever we take equals to 1, so it gives you 0. Similarly, here it is fx1, x0, it should be 1 here, and then x0 here, whole divided by f of x1 minus f of x0. So here you can see, in order to obtain the value for the x2, we must know the value at x0 as well as x1. So that is why initially we had assumed that there exists two initial starting guess in order to proceed for this particular method. So this is the reason why do we use the two initial starting guess. Now this formula looks similar to the regular Falsy method's formula. If you remember, there we had derived a similar nature of formula, but of course this is not the same as that of your regular Falsy formula. The regular Falsy methods works differently, and this method also works differently. So here you can see in the whole procedure we are not checking the sign of the value of the function, while in the case of the regular Falsy method there we had checked the sign of the function, and then we decide which part of the domain we have to keep and which part of the domain we have to left. Here there is nothing like that. So the important thing is, just by changing the index, you can proceed to the next better approximation. And second important thing is, in the regular falsing method or in the bisection, there we have observed that if one value of the function is appearing in the above the x-axis, the other should be below the x-axis. Here you can take both the values above the x-axis or both the values can be below the x-axis. There is no restriction that we are choosing those two values which are one of them is below the x-axis, which one is giving the value of the function below the x-axis and the other one is giving you the value of the function above the x-axis. So there is no such condition in this method of secant. So after knowing all these things, now we apply it. You will see the application of this formula to the solution of the problem is quite simple. So let's start solving the question. Here we take the function fx is equals to x cube minus x minus 11. And the two initial starting guesses are x0. Here we take x0 is equals to 2 and x1 is equals to say 3. So these are the two initial starting guesses from where we are going to take start. And here whenever we want to check the value of the function at x0, so taking x0 equals to 2 into the whole function, this gives you 2 cube 11, this is equals to minus 5. And similarly the other function's value at x1 is f of 3, this gives you 3 cube 3 minus 11 and this gives you 13. So these are the values of the function at the two initial guesses which we have to use in our recurrence formula. The recurrence formula for the secant method is secant method formula. The formula is xn plus 1 xn f of xn minus xn xn minus 1 and whole divided by fxn and f of xn minus 1. Okay. So this is the formula we have to keep on in memory and we can use it in order to look at the root of this. Now to take start of the recurrence formula, we put n equals to 1 because the value of n starts from 1 and on. We can write it here so that we can show the values are starting from 1 and onward. So on taking n equals to 1, this gives you x2 on the left side, while on the right side gives you x0, fx1, x1, x0, and similarly in the denominator we have x0 and this is n and minus f of it should be 1 here and x0 is here. And now you can see on the right side we have all the information, so we can bring them here. x0 is 2, fx1 is 13, x1 is 3 and fx0 is minus 5. So in the denominator we can also substitute the same, the function value is 13 and minus 5 is here. Now you can use your calculating devices and the result, net result is equals to 2.2778. So this is the result for the first better approximation on the basis of the two initial starting guesses of x0 and x1 up to 4 decimal places. You can increase the decimal places according to your requirement, otherwise this is sufficient. After doing this, the next step is to find out the function's value at the new approximated root, which is x2. So this gives you f of 2.2778. So you have to put this value over here into this functions part. So this gives you 2.27778 whole cube minus 2.2778 and minus 11. So whenever you substitute this value into the function, you get the result is minus 1.4600. So this is the output after the first iteration. So till here, the first iteration completes. Now we have to move to the next level of your iteration. So then we have to replace this n by 2, okay? And note down the changes which I am bringing here. First of all, you have to take n equals to 2. On the left side, this gives you n plus 1, gives you 3 here, okay? Now come on, where there are zeros, those will be replaced by 1. And where there are 1, those will be replaced by 2. So you can see here the changes which I have introduced on this side. Once again, look at it. Whenever we take n equals to 2 into this formula, you can check it here. 2 plus 1 gives you 3. 2 minus 1 gives you 1. x2 is here. x2 minus 3 minus 1 2 minus 1 gives you 1 here, and similarly f of x2 here, f of x1 here. Now we can substitute the values. Whenever we put in the values, what do we get? x1 is 3, f of x2 is 2 minus 1 point, we have just calculated, minus 1.46, and x2 is 2.2778, and f of x1 is 13 whole divided by minus 1.46 and minus 13. Okay. Now you can simplify it. The result is equals to 2.3507. Okay. Then you have to calculate the function's value at the new approximated root, which is 2.3507. And the result takes the form 2.3507 whole cube, 2.3507 and minus 11. Now you can see, on putting these values into the main function, we get, after simplification, the results take the form minus 0.3612. So this is your second better approximation. Now we proceed for the next approximation. We solve it here. Okay. For the next iteration, we have to change or replace n equals to 3. In place of n equals to 2, we are taking n equals to 3. So on the left side, this gives you x4. On the right side, this will be x2, fx3, x3, f of x2, whole divided by fx3 and fx2. So this is the change on the right hand side after taking n equals to 3. Now we substitute the values. Whenever you substitute the values, x2 is, we had calculated, this was 2.2778. This was the value of x2. The function value is minus 0.3612 minus x3. x3 is, we have just calculated, this is equals to 2.3507, and the function's value of f of x2 is, we had already calculated, that was equals to minus 1.46. And whole divided by minus 0.3612 and minus 1.46. So here this is the results of 4. Now we simplify the result, we get it is equals to 2.3747. So this is the output after the third iteration. Okay. Now we proceed for the next iteration. I hope you have this formula in your mind and we can now make the change very easily. Okay, I erase all these from here. Okay, now we have to calculate the function's value at the new approximated root, which is x4. So it gives you f at 2.3747 is equals to 2.3747 whole cube, 2.3747 minus 11. And then you have to simplify the result. It is equals to 0.0163. Now we move to the next iteration, number 4. On taking n equals to 4, we get x5 on the left side. On the right side, we'll be having x3, x4, x4, fx3, and whole divided by fx4 and fx3. So this is the changing the formula after changing the index for n equals to 4. And then you have to put in the values. X3 was equals to 2.3507. Fx4 is, we have just calculated, 0.0163. And x4 is 2.3747. And the value of the function of f of x3 was minus 0.3612. Okay, and in the denominator we have 0.0163 and minus 0.3612. Okay. And on simplifying, we'll be having the next better approximation in the form of 2.3736. And the function's value at the next approximation is fx5, which is 2.3736. Will be on substituting it back into the function, we'll get minus 0.00, and one more 0 is there, and 2. And you can see the function value is approaching towards 0. And it is quite obvious that the procedure is converging, and whenever as we move towards the root, of course the function's value must approach towards the 0. So this was the 5th iteration, and we got this output for our function's root. And now if you make the comparison with the previous result, previous approximation, so here we have almost 2 decimal place accuracy. If we perform one more iteration, let's see what happens there. On taking n equals to 5, we'll be having x6, x4 is here, f of x5, x5, f of x4, whole divided by fx5 and fx4. Okay. On substituting the values. So we are now putting in the values. X4 is 2.3747. Fx5 is minus 0.0002. We have just calculated. Minus 2.3736 and 0.0163 is the value for fx4. Whole divided by minus 0.0002 and minus 0.0163. On simplifying, you will be getting a result 2.3736. Now you can make the comparison. You can see here we get the same output as we got in the previous output. So whenever you are approaching or reaching to a place wherever the 2 consecutive iterations gives you the same answer up to the 4 decimal place, so you can take stop. So through this method you have learned how actually the method proceeds. The important thing is the formula. You have to keep the formula in your mind. And second important thing is the initial starting guesses. If you have both of these things clear in your mind, then of course you will be able to find out these questions very easily. And that was the whole story about the secant method. And with this, thank you very much and Assalamu alaikum.